Okay, we're going to be starting chapter 7 here today. This is the chapter that involves exponential functions and then logarithmic functions, which is typically a pretty challenging topic here. But we're going to start with exponential functions. Exponential functions are equations where your variable is actually in the exponent. Most of the equations that we have been working with have had the variable not in the exponent. So for example, like y equals mx plus b, you can see that's not in the exponent. We spent a great deal of time talking about quadratic functions. Here you can see that those variables are not in the exponent. But then if I were to give you an equation maybe that looked like this, you can see now the variable is actually in the exponent. And that's what we mean by exponential functions. And there's a couple of terms that you want to make sure that you're familiar with. The actual number that has the variable in its exponent, we call that the multiplier. Okay, that is the multiplier. And then obviously the x that is in the exponent, that is referred to as the exponent. Sometimes there's also an additional number in front of your multiplier, like in this example here that I wrote, there's a 2, and we'll talk what the meaning of that number is, particularly in the context of the graphs, as well as in the context of some of these word problems. So there are really two types of exponential functions. You can either have exponential growth functions, or you can have exponential decay functions. Now here's the difference. The difference is in your multiplier. So you want to be looking at that base number, the number that has the variable in the exponent. If that multiplier is greater than 1, okay, that is exponential growth. But if that multiplier is a fraction between 0 and 1, that's going to designate exponential decay. Now, in terms of actually looking at the graph, these graphs tend to be pretty flat to begin with if it's exponential growth, but then very quickly they spike, okay, and they get bigger very, very rapidly, okay? So if it's flat and then it rises quickly from left to right, that is exponential growth. If it starts out with a pretty steep slope and then you notice it tends to flatten out as you move from left to right, that's when we're talking about an exponential decay graph. Okay, just to give you a couple examples here. If this equation were, say, y equals 2 to the x, you can see how there my multiplier is a number bigger than 1. That would be an example of exponential growth. But if it were y equals 1/2 to the x power, there my multiplier is a number between 0 and 1. That would be exponential decay. And so all we're going to do here in this first example is we're simply going to designate whether we think these equations here are representing either exponential growth or exponential decay. And again, your focus needs to be exclusively on the number that is the multiplier. Okay, the multiplier is the number that has the variable in the exponent. Okay, so the 2.5. All right, since 2.5 is definitely a number greater than 1, we're going to write down that this is exponential growth. Okay, in the next example, 0.9, well, that's a number between 0 and 1, so we're going to categorize this one as being exponential decay. Okay, and then our last one, our multiplier is a number greater than 1, so then this one is exponential growth. Okay. That's relatively simple to just kind of look at the equation and categorize what type of exponential growth or decay you're dealing with. But let's take a look at how these graphs look and what the numbers, particularly the numbers in front of your multiplier, are telling you about the graph itself. Okay, and that's kind of designated over here. So the A, as we refer to it, the number in front of the multiplier, that is actually telling you where your graph is going to cross the y-axis. So as you look at example A, you'll notice that it feels like maybe there isn't a number in that position for the A, but if there's not a number there, we assume that the A is a 1. Okay, that's what we're assuming is right in front of that 3. Okay, that tells us that this 1 that we're seeing right there is the y-intercept for this graph. So I'm going to go ahead and mark off up to 1 on the y-axis. I'm going to go ahead and put a point there at 1 because I know that this graph is definitely going to cross the y-axis at 1. Okay, the next thing I want to look at is I want to look at my multiplier. Okay, the multiplier is the b value. That's going to tell me whether this is growth or whether it is decay. It's also going to indicate how steep my graph should be. Okay, the bigger the number, the more rapidly it's going to grow, if we're talking about exponential growth. And so I can tell that since this is a 3, it's a number bigger than 1, I would definitely be categorizing this first graph as being exponential growth. Now, something you should know about these graphs, and you can see it up here, these graphs actually do not touch the x-axis. Okay, there's almost like a horizontal asymptote located right on the x-axis. So the graph is ever close to the x-axis, but it doesn't touch it. It's just kind of hugging it and hovering over it. So when we draw these graphs, we want to make sure that they're never actually touching the x-axis. And then I would want to draw it rising very rapidly from left to right. Okay, let's go ahead and try this next one. We'll do this next one a little bit faster here. I can see the a value is a 3, so that tells me that this graph is going to cross the y-axis at 3. And then I also can see that the multiplier is a 3 as well, so that means this is also going to be exponential growth. Okay, so maybe it would start over here, and then I'm going to run through that, and it would rise up quickly. Okay, looking at these bottom 2 examples, I can see that in this example here, the a is a 3, and when I don't actually see a number in front, that means the a value was a 1. So for this graph, it's crossing at 1. This graph over here, it's going to cross at 3, but the difference on these 2 graphs is now the multipliers are numbers between 0 and 1. That means we're talking now about exponential decay. Notice as I'm drawing these decreasing from left to right, I'm still making sure that the graph is not actually going to touch the x-axis. It's just going to hug it or get kind of close to it there. Okay. All right. So we take a look at exponential growth and exponential decay graphs. Let's look at this in the setting of some word problems here. Okay. So one thing that you definitely want to make sure that you're comfortable with is the different parts and pieces to these formulas. Okay. Now on the front, we were writing exponential equations as a times b to the x. In the back, you'll notice here that there's still this a in front, and we had mentioned that that a represents the y-intercept on the graph, but in the context of a word problem, what that a value represents is it represents the initial population. Okay? These problems are going to talk about starting out with an initial amount of something. And so whatever that initial amount is, that's our initial population. And if you look back at the graph, this is y, that's considered the initial population. The initial population is that y-intercept. And what all of these y-intercepts have in common is they all have x-coordinates that are zeros. Okay, so usually in exponential growth and decay problems, your x variable represents your element of time. So if you're talking about a time of 0, you're talking about initially something taking place, okay, right at time 0, and then whatever the y value is, that would have been the initial starting value that you began with, okay? So you want to keep in mind that number in front is the initial population. Of course, your exponent, I'm using a t here instead of an x. The exponent traditionally represents that element of time, okay? And then lastly, you'll see instead of a b here, I have either 1 plus r or I have 1 minus r. Now, collectively, the 1 plus r is what we would call the multiplier, or the 1 minus r over here. But if I go inside the parentheses and I look at just the r value itself, that is what we would call the growth rate if it's 1 plus r. And it's a decay rate if it's 1 minus r. Okay, so let's put this into action here with this first example. Okay, in this first example, it says, after 24 hours, you are really sick. You begin taking an antibiotic that eliminates 20% of the bacteria per hour. Okay, I see that word eliminates. That makes me feel like this problem's talking about something getting smaller, not something growing. The initial population of bacteria is this 1 million number. Okay, notice they told us that was the initial. Remember, that's what our A is in these equations up here. First, we're asked just to write an equation that models the bacterial decay. Yes, when you guys take an antibiotic, usually it doesn't take very long, a day or two, and you are really feeling better, and yet the doctor always says that you should keep taking that medicine for the whole prescription, all 7 days, all 10 days. But it really does wipe out the bacteria or the virus that's in your system pretty rapidly. Okay? And so that's what this is dealing with, a bacterial decay problem. So when we write our equation, I'm going to go ahead and put A of t. You could put y here if you wanted. Okay, I'm going to fill in the initial population of the bacteria. That's that 1 million number. That's my A. Now, if it's a decay problem, I'm going to be over here, and I'm going to want to do 1 minus my decay rate. Now, something I should have you write here. When you write these rates, you want to write them as a decimal. Okay, if it's a growth or if it's a decay, you always want to write it as a decimal. But in the problem, it's going to give it to you as a percentage. Okay, so when we fill this in, we're going to be doing 1 minus, and then I'm going to fill in, the decay rate is 20%, so I'm going to fill in 0.20 for my R, and then I'm going to leave a t as my exponent. When you're asked to write the equation, your equations should have a y in it, which is our A of t, and they should have an x in it, which is what our t is. Okay? So if I were to simplify this, my working equation would be this 1 million number, and then technically the multiplier would be the number 0.80. And I'm just getting that from subtracting the 0.2 from 1. Okay, so I'm going to go ahead and highlight this. This is the equation that we're going to use to answer the other parts to this problem. They're asking, how are you feeling after 1 day, 2 days, 3 days? Now, make sure that you're careful. In this problem, our element of time, it is defined as hours. Okay, so when we're trying to figure out what's the bacterial population in your system after 1, 2, and 3 days, we don't want to plug 1, 2, and 3 in for the t. We want to plug 24 in, 48 in, and then 72 in, because that is the equivalent of how many hours there are in 1, 2, or 3 days. Okay. All right, so we're going to go ahead on the calculator. We would type this in, substituting 24 in, and then 48, and then 72. Okay, so I will go ahead and do that here very quickly, and we can write down what the population of bacteria would be in your system after this time frame here. Okay, so it looks like after 1 day of being on the medication, it's already dropped. You've got 8,449.5 bacteria. 2 days, 39.902, and wow, 3 days, virtually almost completely eliminated from your system. Okay. All right, let's try a second problem here. It says the first U.S. Census was conducted in 1790. At that time, the population was, this feels like this is our initial population, that 3 million number. Since then, the U.S. population has grown by approximately 2.03% annually. So I'm going to circle that percentage. Definitely feels like this is a growth problem. So we're going to be over here. The only difference between setting these up is just on this one you use addition, and on the decay problems you use subtraction. Okay, so let's go ahead and set this up. I'm going to do A of t. I'm going to put the initial population. That's going to be my A. Okay, and then I'm doing 1 plus. Now make sure you're careful. If it's given to you as a percentage, you need to move that decimal point 2 places to the left so that you're shifting it into a decimal and not a percent. Okay, always leave your t as your exponent, and then we can kind of clean this up and write this as 3,929,214. The multiplier is 1.0203 to the t power. Okay, and I got that from just adding 1 and this decimal together. Combined together, that makes my multiplier. I'm going to highlight that, and that's the equation I'm going to use to answer part B. It says, find the population in the year 2020. Okay, now let's look back here. It says the first U.S. Census was conducted in the year 1790. Okay, so we need to figure out what's the difference between the year 2020 and 1790. That is a 230 years later. Okay, so I'm going to want to take my equation right here. I'm going to want to plug 230 into that equation. And it looks like we would get, wow, really big number here. Go back and put some commas in. 399,686,622.6 people is what's projected in the year 2020. Okay. And then finally here in part C, it says, what is the y-intercept of this graph if you were to graph it? Okay, well, let's look back at our equation. Remember, that initial population number, that is also the y-intercept. That's what we said on the front of the notes page. So the y-intercept always has 0 as your x, and then this would be the y-intercept. Okay. All right, we're going to look at one last problem here. We're going to end with example 6 here. Okay, here this is talking about if you were to drink a caffeinated soda, talks about how as time passes, caffeine is eventually eliminated from your bloodstream. And so this feels like it's probably going to be a decay problem. It says it is eliminated at a rate of 15% per hour. So I'm just going to make a little note off to the side that my t or my x variable is in hours. All right, it says a teen drinks a caffeinated soda and the caffeine in his or her bloodstream reaches a peak level of 30 milligrams. So this would be initially, right after you drink the soda, this is how much caffeine you have in your system initially. So this is what we're talking about. This is the initial population of the caffeine in your system. All right, so I'm going to make my equation here. The initial amount is 30. Okay, and then this is a decay problem, so I'm going to be doing 1 minus. I want to look for that percentage, fill it in here, but write it as a decimal, and then my exponent is going to be a t. Okay, I'm going to go ahead and rewrite this. I'm going to simplify what's in the parentheses so that if I were to do 1 minus 0.15, I'm going to get my multiplier to be 0.85. Okay, now this is asking what would be the amount of caffeine in your system after 1 hour, 4 hours, 12 hours, and then 24 hours. Now, since this was defined in hours, I can go ahead and use those numbers. I don't have to do what we did before and kind of convert days into hours here. All right, so we need to type these values into our calculator and do this substitution here. Okay, so after 1 hour, still have 25.5 milligrams. 4 hours, we're down to 15.66 milligrams. Looks like after 12 hours, we are at 4.27 milligrams. And finally, 24 hours, it's virtually out of our system, 0.607 milligrams. Okay. You don't have to worry about example 7 here, but there should be a worksheet that you would be able to print if I did not give this to you in advance. Worksheet 7.1, you could print that off my web page.